Some of the big questions are around what the Earth is going to look like in 2050, 2100. Turns out two of the big uncertainties in that question are how are these aerosol particles cooling the Earth, and so as they go away, how much warming gets unmasked? And the other aspect is, as we warm the Earth, how do the clouds respond? I'm Duncan Watson-Parris. I'm an atmospheric physicist. I have the privilege of working here at Scripps as a climate scientist, trying to understand the role of clouds in the climate system. One of the driving questions in our lab is around the details of how microscopic aerosol particles, which are emitted from burning fossil fuels, interact with the climate system. Actually, one of the biggest challenges, like, how do I make this climate model look like the real world? What parameters do I need to change in there to make them look realistic and therefore more trustworthy and more accurate in their predictions? And we started using more machine learning tools to do that, to make that easier and to actually build surrogate models or emulators of these climate models to enable us to do what we call the inverse problem of learning how to make that model look like the real world data. Being able to quantify this esoteric process enables us to make better projections about what our future will hold and how much warming we will experience. To be clear, we as humans have the most role over where we end up, but given a set of emissions, we want to be able to be as precise as possible about what those choices will mean for our kids, I guess. For these big complex models, we need a lot of compute. We have the San Diego Supercomputer Center on campus. We use the Expanse machine. Scripps itself is special, right? Scripps is one of the oldest oceanographic institutes in the world. It's a privilege and an honor to be here.